13,800,000,000 years ago, everything began. That's what they told us. A point of infinite density, infinite temperature, an explosion from nothing that spawned space, time, matter, every atom in your body, every star in the sky, every galaxy, all of it emerged in that single moment, the moment of creation, the Big Bang. But the mathematics screamed otherwise. The equations exploded. Physics stopped working. At the point of beginning, every law of nature transformed into nonsense. Infinities where there should be none. Division by zero. Temperature beyond any limit. Albert Einstein, the architect of relativity itself, despised this idea, called it abhorrent, refused to believe the universe could be born from mathematical absurdity. Stephen Hawking in the 1970s proved a theorem that shook the physics community to its core. He demonstrated mathematically that if you wind time backward, the universe inevitably collapses into a point of singularity, a point where the laws of physics die, where time loses meaning, where you cannot ask what came before because the very concept of before ceases to exist. The mathematics was elegant, but it was a dead end. For decades, scientists harbored cosmology's dirty secret. The Big Bang cannot be the true beginning. It's physically impossible, but there was no alternative. The data pointed to a hot birth 13 billion years ago. Cosmic microwave background radiation confirmed it. The expansion of galaxies proved it. Yet the point of origin itself remained forbidden territory, a place physics could not penetrate. They were right to doubt. March 22, 2003, a spacecraft transmitted a map to Earth, a map of the universe's most ancient light that had been traveling for 13 billion years. And in that map, scientists saw something impossible. Patterns, structures, information that should not exist, signals from a time before the hot Big Bang. Over the past 20 years, we've assembled the evidence. Each new telescope added pieces to the puzzle. The Planck spacecraft in 2013 confirmed the findings. Ground-based observatories detected anomalies. And in 2024, the James Webb Space Telescope found galaxies that don't fit the standard model. Galaxies too old, too massive, too evolved for their age, as if they remember a time before our universe's hot birth. The truth proves stranger than any fiction. Before the moment we call the Big Bang, there existed another universe, cold, nearly empty, expanding incredibly slowly for trillions upon trillions of years. Then something happened. A quantum field permeating space suddenly released colossal energy. In a fraction of a second, shorter than imagination can grasp, this cold, dark universe transformed into a fiery inferno. Temperature rocketed to trillions of degrees. Space expanded by 10 to the 26th power. It wasn't an explosion. It was a phase transition, like water turning to ice. Except here, emptiness transformed into matter. What you'll learn over the next 2 hours will reshape your understanding of reality. I'll show you why physics broke at the point we called the beginning, what evidence satellites found in the 2000s, and what it means, how the universe actually looked before its hot birth, where all the energy came from to create trillions of galaxies from near-empty space, why James Webb keeps finding objects older than the universe's calculated age, and what all of this means for us, tiny beings on a minuscule planet, trying to understand where we came from. This isn't speculation. This isn't philosophical musing. These are scientific facts backed by observations, mathematics, experiments. The story I'm telling is based on Nobel laureates' work, data from space missions costing billions of dollars, research from thousands of scientists worldwide. Subscribe to this channel because what you're about to hear sounds insane, but every word can be verified. 1927, Belgium. A Catholic priest and physicist named Georges Lemaitre sits in his office, staring at Einstein's equations. The recently published General Theory of Relativity describes how space and time curve under matter's influence. The equations are elegant, but they predict something strange. The universe cannot be static. It must either expand or contract. Lemaitre follows the mathematics wherever it leads. If the universe is expanding now, it must have been smaller in the past. Earlier still, even smaller. If you wind time back far enough, all matter, all energy, all space must have been compressed into an incredibly small volume. Lemaitre calls it the primeval atom, the moment when everything began. He publishes a paper. The scientific community's reaction ranges from skepticism to outright contempt. Einstein, meeting Lemaitre at a conference, tells him point blank, "Your calculations are correct, but your physics is abominable." For Einstein, the idea of time having a beginning reeks of religion, mysticism, everything physics should avoid. The universe is eternal. Most scientists of that era believe this. The notion of creation seems like medieval superstition, but nature doesn't care about our preferences. space. In 1929, Edwin Hubble, observing distant galaxies through the world's largest telescope, discovers an astonishing fact. Galaxies are rushing away from us. Moreover, the farther the galaxy, the faster it recedes. The galaxies aren't moving through space. Space itself is expanding, stretching the distances between galaxies. Einstein is forced to admit his error. He calls his introduction of the cosmological constant an attempt to make the universe static, the biggest blunder of his life. The irony is that 80 years later, this same constant would return to physics with an entirely different role, but more on that later. By the 40s, the scientific community reluctantly accepts the expanding universe. If space is stretching, it's logical to assume it was smaller in the past. Winding time backward, we arrive at a moment of colossal density and temperature. Physicist Fred Hoyle, a fierce opponent of this idea, dismissively calls it the Big Bang during a radio broadcast. The name sticks. Hoyle would spend the rest of his life battling the concept whose name he himself coined. The decisive proof arrives by accident. 1965. Two engineers, Arno Penzias and Robert Wilson, are calibrating an antenna in New Jersey to study radio waves from space. They're irritated by persistent noise in the receiver. Wherever they point the antenna, this noise is present. They clean pigeon droppings from the antenna, check all connections, but the noise won't disappear. Turns out they'd discovered the echo of creation, cosmic microwave background radiation, light emitted 380,000 years after the Big Bang, when the universe cooled enough for photons to travel freely. Over billions of years of expansion, this light stretched, transformed from visible into microwave. The temperature of this radiation is minus 270 degrees Celsius, just 3 degrees above absolute zero, but it's everywhere, fills all space, the afterglow of the universe's fiery birth. Penzias and Wilson receive the Nobel Prize. Big Bang theory becomes accepted. Physicists celebrate victory, but sharp minds understand celebrating is premature, because at the theory's heart lies a mathematical catastrophe, singularity. Winding time backward, the universe's density and temperature increase. At some point, they become so extreme that quantum effects begin competing with gravity. We can't describe this region. Quantum mechanics and general relativity, modern physics' two pillars, contradict each other at these scales. And at the very point of beginning, density and temperature become infinite. What does infinite density even mean? It's not a physical quantity. It's a sign that the mathematics has broken down. Stephen Hawking and Roger Penrose in the 70s prove a series of theorems about singularities. Their work is elegant and ruthless. They demonstrate that under very general conditions, if Einstein's relativity is correct, singularity is inevitable. The universe must have begun from a point where all physical quantities become infinite, where time and space are born from. What? From nothing? The mathematics falls silent. This is a philosophical nightmare. How can time have a beginning? What does the moment before the first moment mean? The question is meaningless if time didn't exist. But intuition protests. Something must have been the cause. Something must have existed before. The idea of creation from absolute nothing contradicts physics' fundamental principle. Nothing comes from nothing. Every effect has a cause, but the first effect, the beginning of all causes, it has no cause. This is a logical dead end. Hawking feels uncomfortable with his own theorem. Later, he'll propose an escape. Perhaps time in the early universe wasn't quite real. Imaginary time, like complex numbers in mathematics. In this case, the question what came before loses meaning, like asking what's north of the North Pole. But this sounds like verbal gymnastics, a way to dodge the question rather than answer it. Physicists know when mathematics produces infinities, it usually means we've missed something, that our theory works beautifully within certain boundaries, but beyond those boundaries, something new is required. It was this way with atoms. Classical physics predicted atoms should collapse in a fraction of a second. Quantum mechanics was needed to explain their stability. Same with black holes. Relativity predicts singularity at the center, but nobody believes infinite density is real. We simply don't yet know the physics of quantum gravity. Same thing with the Big Bang. Singularity isn't describing reality. It's marking the boundary of our knowledge, a signpost indicating something happened there that we don't yet understand. But what exactly? What physics governed the universe in that moment? And the crucial question, was that moment even the beginning, or did something exist before it? Throughout the 70s and 80s, these questions tormented the planet's finest minds. Public lectures described the hot Big Bang as established fact, but in academic corridors, at closed seminars, physicists admitted to each other, we don't understand what happened. We have a beautiful theory of what occurred 1 second after the beginning, even 1/1,000,000th of a second, but the actual point zero, forbidden territory. Then came the breakthrough. A young physicist, Alan Guth, in 1980, working at a small university, makes a simple assumption. What if a quantum field with unusual properties existed in the early universe? A field creating not ordinary gravity that pulls things together, but anti-gravity that pushes space apart. If such a field dominated the early moments, The universe wouldn't expand gradually. It would expand explosively, exponentially, doubling in size again and again in minuscule fractions of a second. Goethe calls it inflation, not to be confused with the economic term, though the analogy is the same: rapid, uncontrolled growth. By his calculations, in less than 10 to the minus 35th power of a second, a region smaller than an atomic nucleus could grow larger than the entire observable universe today. This sounds insane, but the mathematics works. More importantly, this idea solves several puzzles that had tormented cosmologists. Why is the universe so homogeneous? Wherever we look, the cosmic microwave background has nearly identical temperature. Differences are thousandths of a percent. But how could opposite edges of the universe equalize their temperature if light from one edge hasn't reached the other yet? They're causally disconnected. This is the horizon problem. Inflation solves it elegantly. Before inflation, the entire observable universe was smaller than a pea. Temperature had time to equalize. Then inflation ballooned this tiny region to gigantic proportions. That's why everything looks uniform. Originally, it was one small, well-mixed region. There's a second puzzle. The universe is remarkably flat. Space's geometry is almost perfectly Euclidean. Parallel lines neither converge nor diverge. This is incredibly improbable. Any slight curvature in the early universe should have amplified. We should see strongly curved space, but we see flat. Inflation explains this too. Take a balloon, draw a pattern on it. The surface is curved. You see it's a sphere. Now inflate the balloon to Earth's size. Stand on the surface. It looks flat. Inflate further to galaxy size. Any curvature becomes indistinguishable. Inflation stretched space so much that any initial curvature became imperceptible. Goethe's idea captivates physicists' imaginations. But his first version has a problem. Inflation starts but can't end properly. Refinement is needed. Andrei Linde in the Soviet Union and independently Albrecht with Steinhardt in the US propose improved versions. By the mid-80s, inflation becomes standard cosmology. But here's the key point Goethe understood immediately. If inflation is correct, the hot Big Bang wasn't the beginning. It was inflation's end, a transition from cold, slowly expanding phase to hot. The inflation field holding the universe in tension suddenly decayed. All energy stored in that field converted to particles. Radiation, heat, temperature skyrocketed to unimaginable values. That's where the hot Big Bang's energy came from. Not from nothing, from the inflation field's energy. And before inflation, there could have been another universe. Cold, nearly empty, or inflation lasted eternally backward in time, or something else entirely. Suddenly a window opened. Time before the hot explosion became accessible to scientific investigation. This was no longer philosophizing. This was physics. Here's the crucial question that haunted Alan Guth from the moment he proposed inflation. If this explosive expansion really happened, would it leave any evidence? Could we possibly detect something that occurred in the first trillionth of a trillionth of a trillionth of a second after time began? The answer seemed hopeless. How do you find fingerprints from an event so ancient, so brief, so violent? Guth realized something profound. Inflation wasn't perfectly smooth. Quantum mechanics guarantees that nothing in nature is perfectly uniform. Even in the vacuum of space, quantum fluctuations constantly appear and disappear, tiny ripples in energy, existing for impossibly brief moments. Under normal circumstances, these quantum jitters are insignificant, microscopic. But during inflation, something extraordinary happens. Those quantum fluctuations get caught in the expanding space, stretched from subatomic scales to cosmic proportions in a fraction of a second. A ripple smaller than a proton becomes larger than a galaxy. These stretched quantum fluctuations become density variations in the early universe, some regions slightly denser than others. And those denser regions, they eventually collapse under their own gravity, forming galaxies, stars, planets, us. The prediction was specific. If inflation happened, the cosmic microwave background radiation should have a pattern, tiny temperature variations corresponding to those quantum fluctuations. The variations should follow a precise mathematical distribution. The power spectrum should peak at certain angular scales. The statistics should match quantum mechanics predictions. This wasn't vague speculation. This was testable physics. Throughout the 90s, scientists built increasingly sophisticated instruments to measure the cosmic microwave background. Balloon experiments launched from Antarctica, ground-based telescopes in remote deserts, each generation of instruments more sensitive than the last. The variations they sought were minuscule, 1 part in 100,000. Detecting them required measuring temperatures to millionths of a degree across the entire sky. Then NASA greenlit an ambitious mission, the Wilkinson Microwave Anisotropy Probe, WMAP for short, a satellite designed to map the ancient light of the universe with unprecedented precision. It launched on June 30, 2001, carried instruments cooled to near absolute zero, positioned itself 1 million miles from Earth, where it could scan the cosmos without interference. For months, WMAP collected data. Every point in the sky measured thousands of times. The team analyzed patterns, checked for errors, ran simulations. What they found exceeded their wildest expectations. March 22, 2003. The team releases the first results. The images are stunning. The entire sky painted in subtle variations of temperature. Red patches slightly warmer, blue patches slightly cooler. The difference? A few hundred millionths of a degree. But here's where it gets interesting. The pattern matches inflation's predictions almost perfectly. The power spectrum shows exactly the features theorists expected. The size distribution of hot and cold spots follows quantum mechanics. The statistical properties confirm exponential expansion in the early universe. It's the kind of match that makes scientists weep with joy. Theory and observation in perfect harmony. The media celebrates. Headlines declare inflation proven. Nobel Prize committees start taking notes. But a few scientists notice something odd, something that doesn't quite fit. There are anomalies in the data. Subtle, easy to miss if you're not looking carefully. But they're there. The largest scales in the cosmic microwave background show less variation than expected. The universe looks smoother on the bigger scales than inflation predicts. There's also an asymmetry. One half of the sky has slightly stronger fluctuations than the other. Statistically, this shouldn't happen. The universe should look the same in all directions. There are also correlations between fluctuations at very different scales. Again, shouldn't exist according to standard inflation models. Most scientists initially dismiss these anomalies as statistical flukes, measurement errors. When you analyze this much data, some weird patterns will appear by chance. It's like flipping a coin a million times. You'll occasionally see 10 heads in a row. Doesn't mean the coin is rigged. The core predictions of inflation still hold. The anomalies seem like minor footnotes, but a persistent group of physicists won't let it go. They argue these anomalies are trying to tell us something. The largest scale fluctuations in the cosmic microwave background correspond to regions that were causally disconnected even before inflation began. They're too big. They shouldn't be correlated at all, unless something happened before inflation, unless those regions were connected in an earlier phase. The argument is subtle but powerful. During inflation, space expanded exponentially. Regions that were close together before inflation got stretched far apart. That's how inflation solves the horizon problem. Things that look disconnected now were connected before inflation. But the largest fluctuations we see are so large that even inflation can't explain their correlation. They must have been set up by something that happened before inflation started. This is the signature, the smoking gun. Information from a time before the hot Big Bang. Patterns imprinted on the universe by a previous phase of cosmic evolution. The cold, slowly expanding universe that preceded our hot birth left its fingerprints in the largest structures we can measure. The Planck satellite, launched by the European Space Agency in 2009, confirms WMAP's findings with even higher precision. The anomalies are real, they're not going away. By 2013, when Planck releases its full dataset, the evidence becomes harder to ignore. Something weird is going on with the largest scales. Theorists scramble to explain. Maybe inflation didn't start uniformly everywhere. Maybe there was a previous contraction phase. Maybe we're in a multiverse, and these are boundary effects. The possibilities multiply. But one interpretation gains traction. The inflationary period itself had a beginning. Before inflation started, the universe existed in a different state, probably much colder, definitely less energetic, and the properties of that pre-inflationary phase are encoded in the patterns we see today. Let me explain why this matters so profoundly. For decades, the hot Big Bang represented an impenetrable wall. Physics broke down at that point. We couldn't ask what came before because before had no meaning. Time itself began there, or so we thought. But if inflation preceded the hot expansion, then time extended further back. The hot Big Bang wasn't the beginning. It was a transition, a phase change, like ice melting into water. And if time extended before the hot Big Bang, then the question, what came before that, becomes scientifically legitimate. We're no longer doing philosophy. We're doing archaeology, cosmic archaeology, digging through layers of cosmic history to find ever earlier eras. Think about what inflation actually does. A quantum field, spread throughout space, holds an enormous amount of potential energy. This field is in a false vacuum state, metastable, like a ball balanced on a hill. Eventually, the ball rolls down. When it does, the potential energy converts to kinetic energy. In the case of inflation, that energy becomes particles, radiation, heat. The temperature skyrockets. Space fills with matter and energy. That's the hot Big Bang. But where did the inflaton field come from? Why was it in a false vacuum state? How long did it stay there? These questions have answers, physical answers. The inflaton field could have been rolling slowly for an incredibly long time, trillions of years, maybe eternally. During this slow roll, the universe would have been cold, dark, nearly empty, just this quantum field, gradually evolving, causing slow expansion. At some point, through quantum fluctuations or field dynamics, a region of space transitions. The inflaton field begins rolling faster. Inflation kicks in. That region experiences explosive expansion. Inside it, the inflaton field eventually decays, producing our hot Big Bang. But outside, other regions might still be in the slow roll phase, or experiencing their own inflation, or transitioning at different times. This is eternal inflation. Once inflation starts somewhere in the universe, it never fully stops. Even as some regions exit inflation and heat up, other regions continue inflating. The process is self-perpetuating. Inflation creates more space, and that space inflates, creating even more space. It's exponential growth without end. The implications are staggering. Our observable universe, everything we can see, everything that exists as far as telescopes can detect, is just one bubble in an infinite foam, a single pocket where inflation ended and produced a hot Big Bang. But there are other pockets, other bubble universes where inflation ended at different times, with different physical properties, an infinite multiverse, constantly generating new universes. Now here's where your brain starts hurting. If eternal inflation is correct, asking what was the beginning becomes meaningless in a different way. There might be no global beginning, no first moment for the entire inflationary multiverse, only local beginnings like our hot Big Bang, where specific regions transition from the inflationary phase to the hot phase. But wait, doesn't this just push the problem back? If inflation itself is eternal, where did the inflaton field come from? How did the whole process start? Some physicists argue inflation could have begun from a quantum fluctuation in empty space. Others suggest it's truly eternal into the past, no beginning at all. Still others propose that before inflation, there was a contracting universe that bounced into expansion. The honest answer is we don't know. We've pushed the boundary of our ignorance further back in time, but we haven't eliminated it. What we do know is that the evidence, the patterns in the cosmic microwave background, the large-scale structure of galaxies, the flatness and uniformity of space, all point to inflation. And inflation points to something existing before our hot Big Bang. The year 2014 brings another piece of the puzzle. A team of astronomers working at the South Pole announces they've detected primordial gravitational waves in the cosmic microwave background. These waves would be the ultimate proof of inflation, direct evidence of the explosive expansion. The physics community erupts in excitement. Press conferences are called. Social media explodes. Some physicists literally pop champagne. But within months, problems emerge. Careful analysis shows the signal the team detected is actually caused by dust in our galaxy. The supposed gravitational waves are contamination. Embarrassment replaces excitement. The detection is retracted. The search continues. But so far, direct evidence of primordial gravitational waves remains elusive. It's out there somewhere, encoded in the polarization of the cosmic microwave background. We just haven't found it yet. Despite this setback, the overall picture holds. By the mid-2010s, inflation becomes the dominant paradigm. Most cosmologists accept that something like inflation happened. The details might vary, which field, exactly how it rolled, how long it lasted, but the basic mechanism seems solid, and with it comes acceptance of a pre-Big Bang phase. Then the James Webb Space Telescope launches on Christmas Day, 2021. It takes a month to reach its destination, unfolds its massive mirror, calibrates its instruments. When it finally opens its eyes, astronomers point it at the deepest reaches of space, at the earliest galaxies, at the first stars. What Webb sees shakes cosmology once again. Galaxies that shouldn't exist yet. Massive, mature galaxies appearing just a few 100 million years after the hot Big Bang. Galaxies so large, so evolved, so rich in heavy elements that they challenge our models. According to standard cosmology, galaxies should start small and grow over time through mergers and accretion. But Webb sees giants in the cosmic dawn, galaxies that look like they've been around for billions of years, existing in an era when the universe itself was less than 1 billion years old. One discovery in particular sends shockwaves through the community. A galaxy dubbed JWST Z140. It exists just 290 million years after the hot Big Bang, but it's massive, bright, full of stars. How did it form so quickly? Where did all that mass come from? The timescales don't work. There simply wasn't enough time for normal galaxy formation processes to build something that large, unless something happened before, unless the seeds of these galaxies were planted during the inflationary phase, or unless the universe before inflation already had structure, density variations that predated the hot expansion. When inflation ended and space heated up, these pre-existing structures became the foundation for rapid galaxy formation. This is speculative, controversial, Most astronomers prefer more conservative explanations. Maybe our models of early galaxy formation are wrong. Maybe stars formed more efficiently than we thought. Maybe these observations will be revised as Webb collects more data. But a growing minority wonders if Webb is seeing evidence of a rich, complex universe that existed before our supposed beginning. Throughout 2024 and into 25, Webb continues finding puzzles. Supermassive black holes in the early universe, far larger than they should be. Galaxies with chemical compositions suggesting multiple generations of stars, when there should have been time for only one generation. Structures that look mature and organized when everything should still be chaotic and forming. Each discovery can be explained individually, but collectively they paint a picture of an early universe that was far more advanced than we expected, far more ready to form complex structures, as if the universe had a head start, as if the clock didn't really begin at the hot Big Bang, but had been ticking for much longer. The scientific debates are fierce, conferences turn into battlegrounds, papers get published arguing both sides. Some cosmologists defend the standard model, arguing these are just growing pains. We're seeing a new era of cosmic history, and naturally our models need adjustment. Others argue we're witnessing evidence of a fundamental misunderstanding, that our timeline of cosmic evolution is wrong, that the universe is older, in some sense, than we calculated. Here's what makes this moment in science so thrilling. We're not talking about abstract philosophy anymore. We have data, real observations, photographs of ancient galaxies, measurements of the cosmic microwave background, statistics that either fit our theories or challenge them. This is empirical science at its finest. Nature is telling us something, and we're struggling to listen. Let's dig deeper into the mechanics of what actually happened. How does a quantum field sitting in empty space suddenly release enough energy to create everything? The answer lies in one of the strangest concepts in modern physics. The vacuum isn't empty. Even in regions of space with no particles, no radiation, nothing we'd normally call matter, there's still energy. Quantum mechanics demands it. Picture a field stretched across all of space. Think of it like an invisible fabric permeating everything. This field has a value at every point. That value can be high or low, positive or negative. The field wants to settle into its lowest energy state, the way a ball wants to roll to the bottom of a valley. But here's the twist. Sometimes the lowest energy state isn't obvious. Sometimes there are multiple valleys, and the deepest one is hidden behind a hill. The inflaton field found itself trapped in what physicists call a false vacuum, a valley that looks like the bottom, but really isn't, like standing in a crater on the side of a mountain. You're at a local minimum. If you stay still, nothing happens. But if something nudges you hard enough, you roll over the crater rim and tumble down the mountainside to the true valley far below. That's what happened in the early universe. The inflaton field sat in its false vacuum, relatively stable, for an unimaginably long time. During this period, the universe was cold, dark, nearly featureless. Space expanded, but slowly, gently. If you could have visited this pre-inflationary universe, you'd see almost nothing, just emptiness stretching in all directions, maybe the occasional quantum fluctuation flickering in and out of existence, time passing with nothing much happening. Then, through quantum mechanics or field dynamics we still don't fully understand, the inflaton field began to roll, started sliding from its false vacuum toward the true vacuum. And here's where the magic happens. As the field rolls, it releases potential energy. That energy doesn't disappear. It goes into expanding space. The field's energy has negative pressure. Weird, I know, but negative pressure in general relativity acts like anti-gravity. It pushes space apart. The more the field releases energy, the faster space expands. The faster space expands, the more the field rolls. It's a runaway process, exponential, like compound interest on a cosmic scale. The universe doubles in size, doubles again and again and again. In a time period shorter than it takes light to cross an atomic nucleus, a region smaller than a proton expands to larger than a galaxy, then a galaxy cluster, then a supercluster. The numbers become meaningless. 10 to the 26th power expansion, space stretching at rates that make light speed look frozen. During this explosive expansion, something remarkable happens. The energy density stays almost constant. Normally, when space expands, energy density drops. Spread the same amount of energy over a larger volume, and the concentration decreases. But the inflaton field keeps pumping energy into space as it rolls. The energy density remains high throughout inflation. Space is expanding, but it's also being filled with field energy as fast as it grows. Then the field reaches the true vacuum. The rolling stops. Suddenly, all that potential energy has nowhere to go except into particles. The inflaton field oscillates, decays, fragments. Its energy converts into every type of particle the universe can produce. Quarks, leptons, photons, a primordial soup of everything. The temperature skyrockets. Within microseconds, the universe transforms from cold and empty to hot and dense. That transition is what we call the Big Bang, the moment of reheating, when the inflationary energy became matter and radiation. Here's the beautiful part. All the matter and energy in the observable universe, every galaxy, every star, Every atom came from the inflaton field, from the potential energy stored in that quantum field during inflation. Do the calculation. Add up the mass energy of everything we can see. It's enormous, about 10 to the 54th kilograms. Convert that to energy using Einstein's famous equation. You get an almost incomprehensible number. But here's the shock. That entire energy budget could have come from a region of space smaller than a marble. A patch of inflaton field the size of a pea, sitting in its false vacuum, contains enough potential energy to create everything. Because the energy density during inflation is so high, the field is wound up so tight. When it releases, the energy available is essentially unlimited. This solves the biggest mystery about the Big Bang. Where did all the energy come from? If the universe started from a singularity, a point of zero size, asking where the energy came from seems impossible. You can't extract energy from nothing. But if the universe started from a small but finite region filled with inflaton field, then the energy has a source. It came from the field. The field got its energy from, well, that question pushes back one step further. But at least we've removed one layer of mystery. Now you might wonder why the inflaton field was in a false vacuum in the first place. Good question. We don't know for certain. One possibility is that it's random. Quantum fields can find themselves in all sorts of configurations. Some regions of space might have the field in the true vacuum, other regions in false vacuums of various heights. If any region anywhere finds itself in the right false vacuum configuration, inflation starts in that region. And here's where eternal inflation enters. Once inflation begins in one spot, it creates exponentially more space. Within that new space, quantum fluctuations can create new regions where the field climbs back into false vacuum. Those regions inflate, creating even more space. The process never globally ends. Even though individual regions, like ours, exit inflation and heat up, the overall inflationary multiverse keeps generating new inflating patches forever. This means asking when inflation started globally might be meaningless. There might be no beginning to the entire process, only local beginnings, like ours, where specific regions transition from inflating to not inflating. Some physicists find this deeply satisfying, others find it troubling. If inflation is eternal into the past, have we just traded one infinity for another? Replaced the singularity's infinity with eternal time? Not quite. Even eternal inflation might have had a beginning. Alexander Vilenkin and others have proven theorems suggesting that an eternally inflating universe cannot be infinite into the past. At some point, there must have been a boundary, a moment or state where inflation itself began. What that state was remains unknown. Perhaps a quantum fluctuation from nothing. Perhaps a different type of universe altogether. Perhaps something we can't yet imagine. Let's talk about alternatives. Inflation became the dominant theory, but it wasn't the only game in town. Other physicists proposed different mechanisms for solving cosmology's problems without invoking exponential expansion. One idea, championed by Roger Penrose, is conformal cyclic cosmology. Penrose suggests the universe goes through infinite cycles. Each cycle begins with what looks like a Big Bang and ends with the universe expanding forever into emptiness. But Penrose argues that at very late times, when everything has decayed and only photons and other massless particles remain, the universe becomes scale invariant. Without massive particles to define size, the concepts of distance and time become ambiguous. In this state, the far future of one cycle becomes mathematically equivalent to the Big Bang of the next cycle. The universe bounces from end to beginning infinitely. The theory is elegant, poetic even. It avoids the initial singularity by making the Big Bang a transition rather than an absolute beginning. It explains some anomalies in the cosmic microwave background as signals from the previous cycle. Penrose claims to see circular patterns in the CMB data, rings that could be gravitational wave signals from colliding black holes in the previous universe. Most cosmologists remain skeptical. The circular patterns Penrose identifies don't appear statistically significant when you account for how many patterns you could potentially find in random data. The mechanism for transitioning between cycles requires physics we don't understand, and the theory makes fewer concrete predictions than inflation, making it harder to test. Another alternative is the ekpyrotic scenario, proposed by Paul Steinhardt and Neil Turok. They suggest our universe is a three-dimensional membrane floating in higher dimensional space. There's another membrane nearby. Occasionally, separated by trillions of years, these two branes collide. The collision releases enormous energy, appearing to us as the Big Bang. After the collision, the branes separate, and the cycle repeats. This theory emerged from string theory, which predicts extra dimensions beyond the three spatial dimensions we experience. In string theory, our entire universe might be confined to a brane, while gravity can leak into the extra dimensions. The ekpyrotic scenario uses this framework to explain cosmic origins, without traditional inflation. The model has problems. Getting the details right requires fine-tuning the brain's properties in ways that seem contrived. The theory struggles to explain some observations that inflation handles naturally, and like Penrose's cyclic model, it's harder to test observationally. There's also the proposal by Stephen Hawking of imaginary time. Hawking suggested that in the very early universe, time might have behaved like a spatial dimension. Instead of one time dimension and 3 space dimensions, there might have been 4 space-like dimensions. In this scenario, asking what came before the Big Bang is like asking what's north of the North Pole. The question is meaningless because before doesn't exist when time behaves like space. The mathematics works. You can write down equations describing a universe that smoothly transitions from 4 spatial dimensions to 3 spatial plus 1 temporal dimension. The singularity disappears in this formulation. The universe doesn't have a beginning in time. It has a boundary in space-time, but that boundary is smooth and finite, like the surface of a sphere. But here's the challenge. Hawking's proposal requires imaginary time, the square root of -1. Time measured in imaginary numbers rather than real numbers. What does that mean physically? How do you interpret a universe where time is imaginary? Hawking himself admitted this might just be a mathematical trick, a way to do calculations without necessarily representing physical reality. These alternatives haven't gained traction among most cosmologists for a reason. They're harder to test. They require more assumptions. They explain fewer observations with less precision. Meanwhile, inflation keeps passing tests. Every new dataset seems to confirm its predictions, or at least not contradict them. The simplest versions of inflation, simple scalar field, simple potential, simple dynamics, match observations remarkably well. But inflation has problems too. The biggest is the measure problem. If inflation is eternal and creates infinitely many pocket universes, how do you calculate probabilities? If literally everything that can happen does happen infinitely many times across the multiverse, what does it mean to say something is likely or unlikely? Every possible observation occurs infinitely often somewhere. The usual tools of statistics break down. There's also the fine-tuning issue. For inflation to work, the inflaton field needs to start with the right energy in the right configuration. The potential energy curve needs the right shape. Roll too fast, and inflation ends before solving the problems it's meant to solve. Roll too slow, and inflation never ends. The parameters need to fall within specific ranges. Some physicists argue this is no better than the fine-tuning inflation was supposed to eliminate. Defenders of inflation respond that the theory is flexible enough to accommodate many different field types and potentials. The basic mechanism is robust, and once inflation starts anywhere in the universe, eternal inflation ensures it continues indefinitely, producing countless pocket universes with varying properties. In this view, we observe a universe fine-tuned for our existence because we couldn't exist in universes with different properties. Anthropic selection does the rest. These debates rage at conferences, in journals, in late-night conversations between physicists. Strong personalities clash. Reputations are staked on different models. It's science, at its most human. Brilliant people arguing passionately about the nature of reality based on limited data and mathematical elegance. What's clear is that the hot Big Bang was not the absolute beginning. Something preceded it. Whether that something was a period of inflation, a previous contracting universe that bounced, a collision of brains, or something else entirely remains uncertain. But the evidence points away from a singular moment of creation from nothing. Time extends further back than the hot expansion. The universe has a deeper history than we once thought, and that history left traces. The patterns in the cosmic microwave background, the distribution of galaxies on large scales, the flatness of space. These aren't random features. They're archaeological evidence of processes that occurred before conventional cosmology thought the universe existed. We're reading the fossil record of creation, decoding signals from an era that was supposed to be inaccessible. The James Webb Space Telescope's discoveries amplify these questions. Those early massive galaxies suggest the universe was preparing for structure formation even before the hot Big Bang. The seeds were planted during inflation, or perhaps in a phase preceding inflation. When the universe heated up, those seeds immediately began growing. Within a few 100 million years, they'd already produced galactic giants. This is detective work, cosmic forensics. We're piecing together what happened by examining clues left behind billions of years ago. Every new observation adds to the picture, sometimes confirming our theories, sometimes challenging them, always pushing us to think deeper, question harder, imagine more boldly. The energy budget of inflation is staggering when you really sit with it. Consider this. The observable universe contains about 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. Each star is a fusion reactor converting hydrogen to heavier elements, releasing energy for millions to billions of years. The total energy content is beyond human comprehension, and all of that came from a tiny patch of space smaller than a grape, where a quantum field sat in an unstable state. The efficiency is remarkable. Nearly all the inflaton field's energy converted into useful matter and radiation. Very little waste. The universe extracted maximum value from the false vacuum's potential energy. It's like dropping a ball from a great height and having all its gravitational potential energy convert perfectly into kinetic energy. In the real world, friction dissipates some energy, but in the early universe, the conversion was essentially perfect. This tells us something profound about the laws of physics. They're remarkably efficient, remarkably elegant. The process that created everything wasn't messy or chaotic. It followed precise mathematical rules. The inflaton field obeyed differential equations. The energy conversion respected conservation laws. Even in the most extreme conditions imaginable, physics worked predictably. That efficiency raises profound questions. Why are the laws of physics so mathematically precise? Why do they allow for such elegant processes? A slight change in any fundamental constant, and inflation might not work. The inflaton field might never decay properly. The energy conversion might fail. We wouldn't exist to wonder about any of this. Some physicists see design in this elegance. Others see selection bias. If the laws were different, we wouldn't be here to observe them. Across the infinite multiverse generated by eternal inflation, every possible combination of physical laws might exist. We find ourselves in a pocket universe with laws permitting our existence because those are the only universes where observers can arise. Anthropic reasoning applied to cosmic scale. But let's step back from abstract philosophy and focus on what we actually know. The cosmic microwave background contains information, real, measurable data about conditions in the early universe. Every hot spot and cold spot in that ancient light tells a story. The largest structures in that pattern, features spanning more than 10 degrees across the sky, represent regions that were already correlated before inflation even began. Think about what that means. Inflation solves the horizon problem by proposing that causally disconnected regions were actually connected before rapid expansion separated them. A tiny region, small enough for light to cross and establish thermal equilibrium, suddenly balloons to cosmic proportions. That's why opposite sides of the sky have the same temperature. They were neighbors once. But the largest anomalies in the CMB are bigger than inflation's causal horizon. They represent correlations across distances that even inflation can't explain through simple thermal contact. Something must have created those patterns before inflation started. Some process in the pre-inflationary era imprinted structure on the quantum fields that would later become our observable universe. What could that process have been? One possibility is that the pre-inflationary universe wasn't completely uniform. Maybe it had structure, density variations, temperature gradients. These features existed in the cold, slowly expanding phase. When inflation kicked in, it didn't erase these pre-existing patterns completely. It stretched them, amplified them, but preserved their basic structure. After inflation ended and the universe heated up, these ancient patterns influenced how matter distributed itself. Another possibility involves quantum effects in the pre-inflationary state. Even a cold, nearly empty universe experiences quantum fluctuations. These fluctuations normally average out to zero over time. But if the pre-inflationary phase lasted an extremely long time, trillions of years or more, rare quantum events could have created lasting effects. Fluctuations that normally would be statistically insignificant could grow important over such vast timescales. Loop quantum cosmology offers yet another explanation. This approach applies quantum mechanics to the fabric of space-time itself. According to loop quantum gravity, space isn't continuous but made of discrete units, tiny loops of space-time, each one at the Planck scale, knitted together to form the cosmos. In this framework, the Big Bang singularity might be replaced by a quantum bounce. A previous contracting universe reaches a minimum size, not zero, but very small, and rebounds into expansion. If our universe came from a bounce, the pre-bounce phase could have left signatures. Patterns from the contracting era might survive the bounce and appear in the expanding phase. The CMB anomalies could be echoes of that previous universe, memories encoded in the quantum structure of space-time, carried through the bounce like information on a hard drive surviving a computer restart. These ideas remain speculative. The mathematics is challenging. The predictions are often ambiguous, but they represent serious scientific attempts to understand observational anomalies. Physicists aren't ignoring the data, they're working hard to explain it. Now let's address the elephant in the room, the multiverse. If eternal inflation is correct, our observable universe is one bubble in an infinite foam. Each bubble is a pocket universe where inflation ended, creating a hot Big Bang. But the bubbles are separated by exponentially expanding space that continues inflating. We can never see other bubbles. They're causally disconnected, beyond our cosmic horizon. Light from those universes can never reach us. This troubles many scientists. A theory that predicts unobservable universes feels uncomfortably close to metaphysics. How do you test a hypothesis about things you can never detect? If the multiverse exists but remains forever beyond beyond measurement. Is it science or philosophy? Defenders argue that the multiverse isn't a theory itself, rather it's a consequence of well-tested theories. We don't propose eternal inflation to explain the multiverse. We propose inflation to explain observed features of our universe, its flatness, uniformity, the spectrum of fluctuations. Eternal inflation emerges naturally from those models. If inflation happened, eternal inflation is almost inevitable. And if eternal inflation is real, the multiverse follows automatically. Moreover, the multiverse might make testable predictions. If bubble universes occasionally collide, those collisions could leave marks on our cosmic microwave background, circular patterns, temperature discontinuities, specific signatures that could be searched for in data. Several teams have looked. So far, nothing definitive, but the search continues. There's also the hope that string theory or quantum gravity will constrain which types of universes can exist. If only certain combinations of physical laws are mathematically consistent, the multiverse becomes more predictive. We might calculate probabilities for different universe types, compare those predictions against what we observe. That would constitute a test. But honestly, many physicists remain uncomfortable. The multiverse feels too convenient, too much like explaining away problems rather than solving them. Why are the laws of physics fine-tuned for life? Because infinite universes exist with every possible combination of laws, and we're obviously in one that permits observers. It's a true statement, but it doesn't feel satisfying. It shifts the question rather than answering it. Others embrace the multiverse enthusiastically. They see it as the ultimate Copernican revolution. First, we learned Earth isn't the center of the solar system, then that our solar system isn't special within the galaxy, then that our galaxy is one among trillions. Now perhaps our entire universe is one among infinitely many. Each step removed us further from a privileged position. The multiverse is the logical endpoint of that progression. Wherever you stand on these philosophical questions, the observational facts remain. The cosmic microwave background has anomalies. The larger scale patterns don't quite match simple inflation models. Early galaxies observed by Webb appear more evolved than expected. These are puzzles demanding explanation, whether that explanation involves pre-inflationary physics, quantum bounces, or something else entirely. Let's talk about time itself. Before inflation, our intuitive understanding of time might not apply. We think of time as a universal clock, ticking uniformly everywhere. But general relativity teaches that time is relative. It flows differently in different gravitational fields. It can stretch and compress. Near a black hole, time slows dramatically. In the early universe, with extreme densities and energies, time's behavior might have been very strange. During inflation, time behaves weirdly in another way. Space expands exponentially, but the energy density stays roughly constant. From the perspective of someone inside that inflating region, time seems normal. Clocks tick regularly. Physics proceeds predictably. But from an outside view, if such a thing were possible, time in the inflating region appears frozen, stretched by the expansion. Events that take microseconds by local clocks might correspond to vast ages in cosmic time. This creates paradoxes when trying to discuss before inflation. Before according to which clock? If inflation is eternal into the past, there might be no global time coordinate that extends infinitely backward. Time might be emergent, arising from the dynamics of quantum fields rather than existing as a pre-existing stage on which events unfold. Some physicists speculate that time has a beginning, but not the way we usually imagine. Rather than a first moment at which time starts ticking, there might be a boundary to time, like the surface of a sphere has a boundary even though there's no edge. You can't ask what's south of the South Pole because the question is geometrically meaningless. Similarly, you might not be able to ask what's before the beginning of time because the question has no well-defined answer within the mathematics of space-time. These are deep waters. The nature of time connects to fundamental questions in physics that remain unsolved. How do we unify quantum mechanics and general relativity? What is time at the Planck scale? Does time emerge from something more fundamental? These questions extend beyond cosmology into the foundations of physics itself. What we can say with confidence is that the hot Big Bang was not the absolute beginning. Time extends further back. Whether infinitely or to some boundary, we don't know. But the universe has a richer history than the simple story of a singular explosion 13.8 billion years ago. This deeper history changes how we think about causation. The common objection to the Big Bang has always been cosmological. If everything came from the Big Bang, what caused the Big Bang? Physics says every effect has a cause, but the first effect apparently has none. It's an exception to the rules, and exceptions bother scientists. Inflation provides a partial answer. The hot Big Bang was caused by the decay of the inflaton field. The inflaton field's energy came from its potential energy in the false vacuum. That's a physical cause with a physical mechanism. We've removed one layer of mystery, but the question just shifts. What caused the inflaton field to exist? What set it in the false vacuum? If inflation is eternal into the past, maybe there's no ultimate cause. The process has always been happening, but that brings its own problems. An infinite past seems to lead to contradictions. questions. If inflation has been going on forever, why did our particular pocket universe form just 13.8 billion years ago? Why not infinitely long ago? The mathematics suggests eternal inflation might have had a beginning after all. Alexander Vilenkin's theorems indicate that an eternally inflating spacetime cannot be geodesically complete into the past. In plain language, if you trace world lines backward in time, they must eventually reach a boundary, a beginning of sorts, even if that beginning isn't a singular point. What was that beginning? Vilenkin suggests quantum tunneling from nothing, the entire universe as a quantum fluctuation. This sounds bizarre, but quantum mechanics allows temporary violations of energy conservation. Virtual particles pop into existence constantly, borrowing energy from the vacuum, then disappearing. Usually these fluctuations are tiny and brief, but in the extreme conditions of quantum gravity, a much larger fluctuation might occur. An entire universe might quantum tunnel into existence. The mathematics is speculative. We don't have a complete theory of quantum gravity to make firm predictions, but the basic idea is that the universe began as a quantum event, a probabilistic occurrence with no underlying cause, because quantum events are fundamentally random according to the Copenhagen interpretation. The universe exists because it was possible for it to exist, and quantum mechanics ensures that anything possible eventually happens. Other physicists reject this idea. They argue nothing comes from nothing, even in quantum mechanics. Virtual particles borrow energy from existing fields. They require a background structure to fluctuate within. To have a quantum fluctuation, you need quantum mechanics, which means you need space-time, which means you need something rather than nothing. The proposal doesn't truly start from nothing. It smuggles in a quantum vacuum, which is not the same as absolute nothingness. These debates touch on philosophy as much as physics. What does nothing mean? Is a quantum vacuum with no particles truly nothing? Or is it something, a field configuration, a state with properties? Can absolute nothingness exist even as a concept, or does the act of conceptualizing it make it something? We're reaching the limits of what science can address. The origin of everything might lie beyond scientific explanation. Not because of limits on human intelligence, but because of limits inherent to the scientific method. Science explains one thing in terms of others, but the ultimate explanation for why anything exists at all might not be reducible to simpler principles. It might just be a brute fact, or perhaps the question is wrong. Perhaps existence doesn't need an explanation. Perhaps the universe exists because non-existence is impossible or meaningless. These are ancient philosophical questions dressed in modern physics terminology. The fact that we're asking them while analyzing data from the James Webb Space Telescope and the Planck satellite doesn't make the answers any easier. What's clear is that our understanding has deepened dramatically. A century ago, we didn't know other galaxies existed. We thought the Milky Way was the entire universe. 50 years ago, we'd just discovered the cosmic microwave background. 20 years ago, inflation was a promising hypothesis. Today, we have detailed maps of the early universe, evidence for pre-Big Bang physics, and theories connecting quantum mechanics to cosmic origins. The pace of discovery accelerates. Webb will continue observing early galaxies, pushing back to even earlier times. Future CMB missions will map polarization with exquisite precision, searching for primordial gravitational waves. Ground-based gravitational wave detectors might eventually detect signals from the inflationary era. Each new observation constrains theories, eliminates some possibilities, opens new questions. We're living through a golden age of cosmology. The universe is revealing its secrets. The story is more complex, more surprising, more wonderful than anyone imagined. Consider what it means to stand on Earth, looking up at the night sky, and know that the light entering your eyes contains information from before time began, at least before time as we conventionally understand it began. The cosmic microwave background photons streaming past you right now were released 380,000 years after the hot Big Bang, but the patterns encoded in those photons, the tiny temperature variations, the statistical correlations, those patterns were created during inflation. And the larger scale patterns were set even earlier, in the cold universe that preceded inflation. You're seeing the past, but you're also seeing something stranger. You're seeing evidence of a time that shouldn't exist according to older theories, a prehistory of the universe. Every telescope pointed at the distant cosmos is a time machine. The farther we look, the further back we see. Webb observes galaxies from when the universe was just a few 100 million years old. But the cosmic microwave background takes us back further still, and the patterns within it, those point to an even earlier epoch. This changes the existential weight of cosmology. For centuries, humans asked where we came from. Religion provided answers involving creation by divine will. Science gradually replaced those narratives with natural processes, stars forming from gas clouds, planets condensing from stellar debris, life emerging from chemistry. But the ultimate question remained: where did everything come from? What started it all? The hot Big Bang seemed to hit a wall. Before that moment, physics couldn't say. Maybe a creator, maybe nothing. Maybe the question itself itself was meaningless. The singularity represented the limit of knowable reality. Beyond it lay mystery or theology, depending on your perspective. Inflation changes this. The hot Big Bang becomes a natural event, a phase transition, the decay of a quantum field releasing its energy. The cause is physical, understandable, calculable. We've pushed the boundary of scientific explanation further back. The realm of mystery shrinks. We can now ask scientifically meaningful questions about what existed before our universe's hot birth. But has the ultimate mystery truly receded? Or have we simply moved it back one step? If the inflaton field caused the Big Bang, what caused the inflaton field? If a pre-inflationary universe existed, what created it? The chain of causation extends further, but does it end, or does it regress infinitely? Some physicists find comfort in the possibility of infinite regress. An eternal universe with no ultimate beginning needs no first cause. Causation extends infinitely into the past. Every event has a prior cause, without exception. The question, why is there something rather than nothing, becomes irrelevant because there never was nothing. There was always something. Others find this philosophically unsatisfying. An infinite past creates its own paradoxes. If the universe has existed for infinite time, how did we arrive at this particular moment? An infinity of time should have elapsed before now, which seems contradictory. Moreover, the second law of thermodynamics suggests entropy increases over time. If infinite time has passed, shouldn't the universe have reached maximum entropy long ago? These are deep philosophical puzzles with no easy resolution. Science can describe processes, mechanisms, chains of causation, but ultimate origins might lie beyond its scope, or perhaps we need radically new concepts. Maybe causation itself is emergent, not fundamental. Maybe time is an illusion arising from quantum entanglement. Maybe the universe doesn't have an origin in the conventional sense because the very idea of an origin assumes a pre-existing time frame. What science can do is rule out possibilities, test hypotheses, narrow the options. We know the hot Big Bang happened. We have overwhelming evidence. We know inflation or something very much like it happened. The evidence is strong and growing. We know time extends further back than the hot expansion. The CMB anomalies suggest this. Early galaxy observations from Webb hint at it. What comes next in our investigation? Several missions are planned or proposed that could revolutionize our understanding further. The Simons Observatory, currently being built in Chile, will map the cosmic microwave background with unprecedented precision. It's specifically designed to detect primordial gravitational waves, the smoking gun signature of inflation. If it succeeds, we'll have direct evidence of the exponential expansion. We'll measure inflation's energy scale. We'll constrain which models of inflation are correct. Lightbird, a Japanese-led satellite mission scheduled to launch in the late 2020s, will measure CMB polarization from space. Free from atmospheric interference, it can achieve sensitivities impossible for ground-based telescopes. If primordial gravitational waves exist at the levels many theories predict, Lightbird should find them. The discovery would rank among the most important in physics history. Direct detection of quantum gravity effects, proof that space-time itself is quantized, evidence of physics at energies far beyond what particle accelerators can reach. CMB-S4, a fourth-generation ground-based cosmic microwave background experiment, will deploy tens of thousands of detectors across multiple sites. It will map not just temperature but polarization patterns with exquisite detail. It will search for signatures of cosmic strings, phase transitions, bubble collisions, any of the exotic phenomena that might have occurred in the early universe. It will test whether the CMB anomalies are real or statistical flukes. If they're real, CMB-S4 will characterize them precisely enough to distinguish between theoretical explanations. Meanwhile, the James Webb Space Telescope continues its mission. Every month brings new discoveries, galaxies at redshift 15, 16, 17, pushing ever closer to the first stars. Detailed spectroscopy of exoplanet atmospheres, searching for biosignatures, studies of the earliest black holes, trying to understand how they grew so massive so quickly. Each observation refines our models, confirms some theories, challenges others. Future space telescopes will go further. The Habitable Worlds Observatory, currently in early planning stages, will directly image Earth-like planets around other stars. While primarily focused on the search for life, it will also study galaxy formation in unprecedented detail. The Nancy Grace Roman Space Telescope, launching in the mid-2010s, will survey vast swathes of sky, mapping cosmic structure on the largest scales. These observations will test inflation's predictions about how matter distributed itself after the universe heated up. On the ground, the next generation of extremely large telescopes, mirrors 30 to 40 meters across, will see first light in the coming decade. They'll observe individual stars in the earliest galaxies. They'll measure the expansion rate of the universe with new precision. They'll study the dark energy that's currently accelerating cosmic expansion. Is dark energy constant, or does it evolve over time? The answer will tell us about the universe's ultimate fate and might provide clues about inflation's mechanism. Gravitational wave astronomy is barely a decade old. LIGO and Virgo have detected dozens of black hole mergers, neutron-star collisions, events releasing more energy and gravitational waves than all the stars in the universe emit as light. Future detectors will be even more sensitive. LISA, the Laser Interferometer Space Antenna, will launch in the mid-2030s. Its 3 spacecraft flying in formation, separated by millions of miles, detecting gravitational waves from supermassive black hole mergers across cosmic history. But there's a possibility that excites cosmologists even more. If LISA, or a similar space-based detector, is sensitive enough, it might detect the stochastic background of gravitational waves from inflation itself. Not the polarization pattern in the CMB, which is an indirect signature, but actual gravitational waves propagating through space. This would be the holy grail. Direct detection of gravitational radiation from the inflationary epoch. We could measure inflation's properties directly, determine exactly how fast the universe expanded, constrain the inflation field's potential energy curve, distinguish definitively between different inflation models. These aren't science fiction proposals. These are funded missions, planned telescopes, serious scientific efforts with realistic timelines. Within the next 10 to 20 years, we'll likely know whether primordial gravitational waves are detectable. We'll have mapped the cosmic microwave background with extraordinary precision. We'll have observed galaxies forming in the first 100 million years of cosmic history. We'll have tested inflation's predictions against data in ways currently impossible. One of 3 things will happen. First possibility: everything matches inflation's predictions. The theory passes every test. Anomalies disappear or are explained. Primordial gravitational waves are detected with the expected characteristics. In this scenario, inflation becomes as well established as the Big Bang itself. We'll know that exponential expansion happened. We'll understand the mechanism. The remaining questions will focus on what caused inflation to start and whether eternal inflation creates a multiverse. Second possibility: observations deviate from simple inflation models but match more sophisticated versions. Maybe the inflaton field's potential energy curve has features that create distinctive patterns. Maybe there were multiple fields involved. Maybe inflation had a more complex history than basic models suggest. This would be exciting because it would tell us details about the inflationary process. We'd learn about the physics at energies trillions of times higher than anything we can create in laboratories. We'd probe conditions that existed in the first trillionth of a second. Third possibility: observations contradict inflation. The primordial gravitational waves aren't there. The predicted patterns don't match data. New anomalies emerge that inflation can't explain. This would force a revolution in cosmology. We'd need new theories. Maybe a bounce from a contracting universe. Maybe something involving quantum gravity we haven't thought of yet. Maybe a completely different mechanism for creating the universe's uniformity and flatness. This scenario would be scientifically thrilling because revolutions lead to breakthroughs. Actually, there's a fourth possibility. Observations might be ambiguous. Different theories could fit the data equally well. This is the frustrating scenario where we need even better instruments, even more precise measurements. But eventually, with enough data, ambiguity resolves. Nature always provides an answer if you ask the right question the right way. Here's what strikes me as profound about this moment in history. For essentially all of human existence, questions about cosmic origins were philosophical or religious. Science couldn't address them. The tools didn't exist. The concepts weren't developed. The observations weren't possible. But in the span of a single human lifetime, yours perhaps, cosmology transformed from speculation to precision science. My parents grew up in a world where we didn't know if the universe was expanding or static, young or ancient, finite or infinite. My grandparents' generation didn't know other galaxies existed. My great-grandparents thought the Milky Way was the entire cosmos. Go back one more generation, and humans couldn't even agree on Earth's age. Some thought thousands of years. Others suspected billions, but couldn't prove it. Now we know the universe is 13.8 billion years old, give or take a few million years. We know it's expanding and accelerating. We know it went through an inflationary phase. We know what it was made of at different epochs. We have baby pictures of the universe, literally photographs of structures forming when the cosmos was in its infancy. This knowledge accumulation is breathtaking. And we're not done. The next generation will know more still. They'll have data we can only dream about. They'll test theories we're currently debating. Some questions we consider mysteries will have clear answers. New mysteries will emerge because every answer generates new questions. That's how science works. Each solved puzzle reveals deeper puzzles beneath, but there's something almost spiritual about this quest to understand our cosmic origins. We're made of atoms forged in stars. Those stars condensed from gas clouds created during the Big Bang. That hot plasma came from inflation's energy. That energy was released by a quantum field rolling down its potential. We're tracing our ancestry back through time, following the chain of causation that led to our existence. Every carbon atom in your body was created in a star that exploded billions of years ago. That carbon was incorporated into a gas cloud that eventually collapsed, to form our solar system. Earth accreted from that material. Life emerged. Evolution proceeded. Your ancestors survived long enough to reproduce. An unbroken chain of causation connects you directly to the inflaton field decay that started the hot Big Bang. You are literally the universe experiencing itself, made of cosmic material, animated by energy that ultimately traces back to inflation. Using a brain built by evolution to contemplate the origin of everything. Carl Sagan said we are star stuff. True enough. But we're also inflation stuff, Big Bang stuff, quantum fluctuation stuff. Whatever process created the universe, we're made from it. Understanding cosmic origins is understanding our own origins at the deepest level. The scientists who discovered these truths about cosmic origins are human beings driven by curiosity, ambition, ego and wonder, just like anyone else. Alan Guth wasn't trying to solve the ultimate mystery of existence when he invented inflation. He was working on a technical problem in particle physics, trying to understand why certain exotic particles called magnetic monopoles hadn't been detected. His inflation idea solved that problem almost as a side effect. The real breakthrough was realizing it solved cosmology's biggest puzzles simultaneously. Andre Linde, who refined inflation theory, describes the moment he understood eternal inflation would create infinite universes. He was walking through Moscow in the middle of winter, and the realization hit him so hard he had to stop on the sidewalk. The implications were staggering. Everything that can happen will happen infinitely many times across the multiverse. Every possible history plays out somewhere. He stood there in the cold, mind reeling, until his wife asked if he was okay. How do you explain to someone that you've just realized our entire universe might be one bubble in an infinite foam? Vera Rubin spent decades fighting for recognition of dark matter, facing dismissal and condescension from male colleagues who couldn't accept her observations. Her careful measurements of galaxy rotation curves showed that visible matter couldn't account for the gravitational forces at work. Something invisible, something dark, must dominate the universe's mass. She was right, but it took years for the establishment to acknowledge it. Her story reminds us that scientific truth doesn't always win immediately. Social factors, prejudices, and institutional inertia slow progress, yet eventually good data wins. Reality doesn't care about our biases. The BICEP2 team thought they'd detected primordial gravitational waves in 2014. They held a press conference. The media exploded with headlines about proving inflation. Andre Linde received the news via a surprise visit from Chaolin Kuo, one of the team members, who knocked on his door with a bottle of champagne and a video camera. Linde's reaction, captured on video, is pure joy. Tears in his eyes, hands shaking, 30 years of hoping, and finally, evidence. Except the evidence turned out to be contaminated by galactic dust. Within months, careful analysis by the Planck team showed the signal BICEP2 detected wasn't primordial. It was foreground emission from our own galaxy. The embarrassment was profound. Papers were retracted. The champagne celebration became a cautionary tale. Science is hard. Even brilliant people with cutting-edge instruments can be fooled. The universe doesn't give up its secrets easily. But that failure taught important lessons. It showed how careful you must be when claiming extraordinary results. It demonstrated the value of independent verification. It revealed how desperately scientists wanted to find that signal, enough that they perhaps didn't question their assumptions as rigorously as they should have. The primordial gravitational waves are still out there, waiting to be found. We just haven't detected them yet. The search continues with better instruments, more sophisticated analysis, greater awareness of potential contamination. This human element of science matters. These aren't abstract equations solving themselves. These are people dedicating their lives to understanding reality. They make mistakes. They experience disappointment. They feel rivalry and cooperation, frustration and triumph. Progress happens through this messy human process, not despite it. Consider Jocelyn Bell Burnell, who discovered pulsars as a graduate student but saw the Nobel Prize awarded to her male supervisor. Or Rosalind Franklin, whose X-ray crystallography data was crucial to discovering DNA's structure, yet she received little credit during her lifetime. Or Lisa Meitner, who explained nuclear fission but was excluded from the Nobel Prize awarded for the discovery. Science has historically marginalized women and minorities, crediting their work to more powerful men. We're only beginning to correct these injustices. The cosmic microwave background's discovery is itself complicated. Penzias and Wilson got the Nobel Prize, deservedly, for detecting it. But Robert Dicke at Princeton had predicted the CMB should exist and was building instruments to find it when Penzias and Wilson accidentally discovered it first. Ralph Alpher and Robert Herman calculated its temperature in the 1940s, predictions that were largely forgotten. George Gamow contributed crucial theoretical work. Who deserves credit? History simplifies complex stories into neat narratives, but reality is messier. These complicated complications don't diminish the science. The cosmic microwave background exists regardless of who discovered it or who gets credit. Inflation either happened or it didn't, independent of human politics. But understanding how science actually works, the human side, the mistakes, the controversies, gives us appropriate humility about our current knowledge. Today's certainties may become tomorrow's cautionary tales. What would it mean if we definitively proved something existed before the Big Bang? Philosophically, theologically, existentially. For some religious traditions, the Big Bang represented the moment of divine creation. God said, "Let there be light," and there was light. If time extends before that moment, does it challenge religious belief, or does it simply push the moment of creation further back? Many theologians and religious scientists see no conflict. If God exists outside time, then God created the pre-Big Bang universe just as much as the post-Big Bang one. The mechanism of creation, whether a singular explosion or a phase transition from inflation, doesn't change the fundamental question of why there's something rather than nothing. Science explains how. Religion addresses why. The two need not conflict. For materialist philosophies, pre-Big Bang physics presents different challenges. If the universe had no beginning, if time extends infinitely into the past, then the question what caused everything might have no answer. Reality might just exist without ultimate explanation. Causation might be a feature of physics within the universe rather than a property of the universe itself. We ask what caused the Big Bang because we're used to events having causes, but perhaps the universe as a whole doesn't follow that rule. Some philosophers argue that existence is necessary, non-existence is impossible or incoherent. Something must exist, and the question is only what kind of something. The universe exists because it must, because the alternative is literally nothing, and nothing cannot be. This sounds like wordplay, but serious thinkers have defended such positions. David Lewis argued for modal realism, the view that all possible worlds actually exist, not just as abstractions but as concrete realities. Our universe is one among infinitely many, each equally real. If eternal inflation is correct, something like modal realism might be physically true. Every possible configuration of physical laws might exist somewhere in the infinite multiverse. Every history that could happen does happen. We observe this particular universe because we're the kind of beings that can exist in this particular universe. Elsewhere, different observers experience different physics. The multiverse is existence exhausting all possibilities. But does this explain anything, or does it just rename the mystery? Instead of asking, why does this universe exist, we ask, why does the multiverse exist? We haven't solved the fundamental puzzle. We've expanded its scope. Some philosophers find this deeply unsatisfying. Science keeps pushing the question back, but never answering it. The mystery of existence remains. Others embrace the mystery. Perhaps ultimate explanation is impossible. Perhaps reality bottoms out in brute facts that have no further justification. Perhaps the question, why is there something rather than nothing, is unanswerable in principle, not just in practice. This doesn't make the question meaningless, but it suggests we should accept limits to explanation. Some things just are. What about consciousness in all this? The fact that the universe produced observers, beings capable of understanding cosmic origins, is remarkable. The atoms in your brain, the neurons firing as you process these words, the subjective experience of comprehension, all of this arose from the laws of physics operating over billions of years. Complexity emerged from simplicity, life from non-life, consciousness from unconscious matter. How? Cosmology doesn't answer that question directly, but it provides context. The universe needed certain properties for life to emerge. If the electromagnetic force were slightly stronger or weaker, atoms couldn't form. If gravity were different, stars wouldn't forge heavy elements. If the strong nuclear force varied, hydrogen couldn't fuse into helium. The universe sits in a narrow range of physical constants that permit complexity. This fine-tuning has multiple possible explanations. Maybe we're in a multiverse, and we observe a life-permitting universe because we couldn't exist in any other kind. Maybe the physical constants aren't arbitrary, but determined by deeper principles we haven't discovered. Maybe there's only one possible universe, and it happens to permit life. Maybe a creator designed it that way. Each explanation has proponents. The anthropic principle, that we observe properties compatible with our existence, is either profound or trivial depending on perspective. Trivially, yes, we must live in a universe that permits life. But profoundly, why does such a universe exist at all? If the multiverse contains infinite universes with varying properties, anthropic selection explains our observations. If there's only one universe, and it's fine-tuned, that requires explanation. String theory suggests that the physical constants we observe aren't fundamental but environmental, like local weather conditions rather than universal laws. Different regions of space-time might have different particle physics, different forces, different dimensionality. We live in a region with the particular physics we observe. Elsewhere, the rules differ. This turns fine-tuning into a selection effect. Observers appear in regions where physics permits observers, but string theory remains unproven. Frustratingly, it makes few testable predictions predictions at accessible energies. Critics call it not even wrong, so flexible it can accommodate any observation, making it unfalsifiable. Defenders argue we simply haven't developed the mathematical tools to extract predictions yet. The theory might be right even though we can't test it with current technology. Or it might be an elaborate mathematical structure with no connection to physical reality. Loop quantum gravity, a competing approach to quantum gravity, makes different compromises. It preserves the smoothness of space-time at large scales while introducing discreteness at the Planck scale. It predicts specific effects that might be observable, slight variations in light speed depending on frequency, signatures in cosmic ray data. Some observations hint at these effects, others contradict them. The jury is out. Whichever theory of quantum gravity turns out correct, it will tell us about the very early universe. It will explain what happened at the Planck time, 10 to the minus 43 seconds after inflation began converting its energy to particles. It will reveal whether singularities truly exist or are mathematical artifacts of incomplete theories. It will possibly tell us what preceded inflation, what started the whole process. Experiments at particle accelerators like the Large Hadron Collider search for clues. Supersymmetry, extra dimensions, dark matter particles, any of these discoveries would point toward quantum gravity. So far, the LHC has found only the Higgs boson, confirming the standard model but not revealing physics beyond it. The next generation of colliders, if built, might probe higher energies, but even the most powerful conceivable accelerator can't reach the energies present during inflation. We're trillions of times too weak. That's why cosmology is crucial. The early universe was a natural particle accelerator, reaching energies no human technology can approach. The patterns in the cosmic microwave background encode information about physics at those scales. Webb's observations of early galaxies test models of structure formation. Gravitational wave detection probes space-time itself. Cosmology and particle physics converge on the same questions from different directions. What happens if we never detect primordial gravitational waves? If the signal is too weak, if foreground contamination always dominates, if the universe refuses to reveal that particular secret, would inflation remain unproven? Or is the circumstantial evidence strong enough? Courts convict on circumstantial evidence when it's overwhelming. Inflation solves multiple problems. It makes specific predictions that match observations. The cosmic microwave background's pattern is exactly what inflation predicts. Galaxy distributions match. The universe's flatness matches. At some point, even without the smoking gun of gravitational waves, the accumulated evidence becomes decisive. But science always craves that direct detection, that unambiguous signal, that single observation that removes all doubt. Until we have it, there's room for alternative theories. Maybe inflation is wrong and something else explains the data. Maybe the universe is actually very different from our models, and we're missing something fundamental. Humility demands we acknowledge these possibilities. Yet even with those caveats, something remarkable has happened in our lifetimes. We've gone from being utterly ignorant about cosmic origins to having a detailed, testable theory. We've traced the universe's history back to fractions of a second after the hot expansion began. We've found evidence pointing to an earlier era. We've transformed philosophy into physics. That's an achievement worth celebrating, even as we acknowledge how much remains unknown. Let me bring this back to the question we started with. What existed before the Big Bang? Based on everything we've discussed, the observations, the theory, the evidence, here's what we can say with reasonable confidence. The hot Big Bang, the moment when the universe filled with matter and radiation at extreme temperatures, was preceded by a cold inflationary phase. During this phase, a quantum field called the inflaton dominated the universe's energy. Space expanded exponentially. The universe was nearly empty, nearly featureless, cold and dark. This phase might have lasted an incomprehensibly long time, trillions of years perhaps, or it might have been brief by cosmic standards, just millions or billions of years. At some point, the inflaton field decayed. Its potential energy converted to particles and radiation. The temperature skyrocketed. Space filled with a hot plasma. That moment is what we traditionally call the Big Bang, though it wasn't the true beginning. It was a transition, a phase change, the birth of the hot universe from the cold one. Before the inflationary phase? That remains speculation. Maybe inflation extended infinitely into the past, with no global beginning. Maybe there was a quantum bounce from a previous contracting universe. Maybe the entire thing started as a quantum fluctuation from nothing, though nothing is a loaded term that might not mean what we think it means. Maybe time itself has a beginning in some geometric sense that doesn't require a first moment. We genuinely don't know. What we do know is that time and causation extend further back than we once thought. The boundary of our ignorance has retreated. The realm of scientific inquiry has expanded. Questions that were philosophical have become physical. We're making progress. Now let's talk about what this means for you personally. You're living at a unique moment in human history. For thousands of generations, Humans wondered about origins. They created myths, religions, philosophies, beautiful stories, many of them, meaningful frameworks for understanding existence. But they were guesses, educated guesses sometimes, based on intuition and reasoning, but guesses nonetheless. You're part of the first generation that knows, really knows, with evidence and mathematics and observations. You live in an era where we can photograph the infant universe, where we can measure the afterglow of creation, where we can test theories about what happened before time began, or at least before the hot expansion started. That's extraordinary. Don't take it for granted. When you look up at the night sky, you're not just seeing pretty lights. You're seeing history. The light from distant galaxies left those galaxies millions or billions of years ago. You're literally looking into the past, and cosmologists can look even further, using radio telescopes to detect the cosmic microwave background. Light that's been traveling for 13.8 billion years. Light that encoded patterns from the inflationary era, from before the Big Bang as conventionally defined. Every photon carries information. The universe is telling us its story if we have the instruments to listen and the mathematics to decode the message. We're reading the autobiography of the cosmos written in light and gravitational waves and the distribution of matter. It's the greatest detective story ever told, and we're living through the most exciting chapters. What comes next? Within your lifetime, we'll likely know whether primordial gravitational waves are detectable. We'll have mapped the cosmic microwave background with extraordinary precision. We'll have observed galaxies forming in the first 100 million years. We'll have tested inflation's predictions thoroughly. One of three outcomes will occur. First, inflation might pass every test. The theory will become as established as evolution or heliocentrism. We'll know that exponential expansion happened. The details might remain debatable, but the basic mechanism will be confirmed. In this scenario, physics textbooks will describe the pre-Big Bang universe as matter-of-factly as they currently describe stellar nucleosynthesis. Second, inflation might require modifications. The data might show unexpected patterns that simple models don't explain. We'd develop more sophisticated theories, multiple fields, non-minimal couplings, connections to string theory or quantum gravity. The core idea that something preceded the hot expansion would survive, but our understanding would deepen and complicate. Third, observations might contradict inflation entirely. We'd need revolutionary new physics. This would be scientifically thrilling, though humbling. It would mean we fundamentally misunderstood cosmic origins. New theories would emerge. Controversies would erupt. Eventually, a new consensus would form around whatever theory best matches observations. That's how science works. Old ideas yield to better ones when evidence demands it. Personally, I find all three scenarios exciting. Confirmation validates decades of theoretical and observational work. Modification means we're learning unexpected things about nature. Revolution means breakthroughs and paradigm shifts. Science wins regardless of which path nature chooses. But there's a deeper level to this. Beyond the technical questions about inflation and quantum fields and gravitational waves, there's the existential question: why does the universe exist at all? We've pushed that question back from the hot Big Bang to the inflationary era, but we haven't answered it. Maybe we can't. Maybe the question transcends science, or maybe not. Maybe the ultimate theory of quantum gravity will explain why universes form. Maybe the mathematics will show that existence is necessary, that non-existence is impossible. Maybe we'll discover that our universe is one fluctuation in an eternal quantum foam, and the question why something rather than nothing will dissolve because there was never truly nothing. These are the questions your generation and the next will grapple with. The tools are being built right now. The theories are being refined. The data is accumulating. Within decades, we'll know so much more than we do today. Your children or grandchildren might grow up in a world where cosmic origins are understood with the same confidence we currently have about planetary motion or genetics. Think about what that means. For most of human existence, our origins were mysterious. We told stories about gods and creation myths. Then we developed science and pushed back the mystery. But the ultimate mystery, the very first moment, the origin of everything, remained beyond reach. Now, in your lifetime, that mystery is crumbling. We're witnessing the moment when humanity finally understands where we came from, all the way back to the beginning, or as close to a beginning as exists. That's profound. That changes how we think about our place in the cosmos. We're not separate from the universe. We're not observers standing outside looking in. We're part of it. The atoms in your body were forged in stars. The energy animating you traces back to inflation. The laws of physics that govern your brain's neurons are the same laws that governed the early universe. You are the cosmos examining itself. Carl Sagan captured this beautifully when he said we're a way for the cosmos to know itself. But it's deeper than poetic language. It's literally true. The universe evolved complexity, stars, planets, chemistry, life, consciousness. Through an unbroken chain of physical processes, matter organized itself into structures capable of reflection. You're one of those structures. When you contemplate cosmic origins, you're the universe contemplating its own origins. There's something almost spiritual about that, even for those who don't believe in traditional spirituality. A sense of connection, of meaning, of participation in something vastly larger than individual existence. You're not just living your life, you're part of cosmic history. The same story that includes the Big Bang and inflation and galaxy formation also includes you. You're a chapter in the universe's autobiography. So what should you do with this knowledge? That's up to you. But here's my suggestion. Share it. Tell people. Explain to friends and family what we've learned about cosmic origins. Show them images from the James Webb Space Telescope. Describe the cosmic microwave background. Make them understand that we're living through one of the most important eras in human intellectual history, the era when we finally answered the oldest questions. Support space missions and telescope projects. They're expensive, yes, billions of dollars. But what price would you put on understanding existence itself? These missions are humanity's most ambitious attempts to decode reality. They deserve resources and attention. Write to representatives. Vote for science funding. Make sure the next generation of instruments gets built. Study this stuff if it interests you. Not necessarily professionally, though we need more scientists, but as a curious human. Read books about cosmology, watch lectures, follow new discoveries. You don't need a physics PhD to appreciate the beauty of these ideas. Popular science exists to make cutting-edge research accessible. Take advantage of it. And when you look at the night sky, remember what you're seeing. Those stars formed from the debris of earlier stars. Those earlier stars condensed from primordial gas. That gas came from the hot Big Bang. The hot Big Bang came from inflation. And inflation, well, we're still working on where inflation came from. But we're closer than we've ever been. The journey from ignorance to understanding is never complete. Every answer spawns new questions. That's beautiful, not frustrating. It means there's always more to discover. Always deeper layers of reality to explore. The universe reveals itself gradually, rewarding curiosity and patience. Right now, at this moment, photons from the cosmic microwave background are passing through your body, millions of them every second, unchanged since 380,000 years after the hot expansion began, carrying information about the early universe encoded in their wavelengths and polarization. You're literally bathed in ancient light. The echo of creation flows through you constantly. In some sense, the universe is always telling us its origin story. We just needed to develop the technology and mathematics to listen, and now we have. We've built radio telescopes sensitive enough to detect whispers from the beginning of time. We've developed theories sophisticated enough to decode those whispers. We've created a coherent narrative connecting the universe's earliest moments to the present day. That narrative will continue evolving. New observations will refine it. New theories will explain previously mysterious details. Future generations will look back at our current understanding the way we look back at Newton's clockwork universe, correct in important ways but incomplete, missing crucial pieces that later discoveries revealed. But the basic story seems solid. The hot Big Bang happened. Inflation preceded it. A cold universe existed before the hot one. Time extends further back than we once thought. The boundary between science and metaphysics has shifted. Questions that were philosophical are now physical. Where that story ultimately leads, we don't yet know. Maybe to a multiverse of infinite universes. Maybe to a quantum origin from nothing. Maybe to eternal inflation with no beginning. Maybe to something we haven't imagined yet. The final chapters remain unwritten, but you're here for it. You're witnessing the discoveries as they happen. Every new James Webb image, every cosmic microwave background analysis, every gravitational wave detection. Each piece of the puzzle slots into place before your eyes. You're living through the golden age of cosmology. So here's my final thought. The question, what came before the Big Bang, isn't just about physics. It's about understanding our place in existence, about knowing where we came from, about connecting with the largest possible story, the story of everything. We've made extraordinary progress on that question. We've discovered that the Big Bang wasn't the beginning. That time extends further back, that a cold, dark, nearly empty universe preceded our hot, bright, matter-filled one. We don't have all the answers yet. Maybe we never will. Maybe some questions transcend scientific inquiry, but we've pushed the boundary of knowledge further than anyone thought possible. We've turned mystery into data, philosophy into physics, wonder into understanding, and the journey continues. The universe still has secrets to reveal. Future generations will discover things we can't imagine. They'll answer questions we haven't thought to ask. They'll push knowledge even further into the unknown, but they'll build on what we've learned, on the observations we've made, on the theories we've developed, on the instruments we've built. The story of cosmic origins is cumulative. Each generation adds to the picture. You're part of that chain, a link connecting past discoveries to future understanding. So the next time someone asks you what existed before the Big Bang, you can tell them, not with certainty about every detail, not with answers to every question, but with evidence, with data, with theories tested against observations. You can explain that the hot expansion was preceded by a cold inflationary phase, that quantum fields release their energy to create everything. That time extends further back than we once thought, and then you can tell them the most exciting part. We're still figuring it out, still making discoveries, still refining our understanding. The story isn't finished. It's being written right now by telescopes in space and observatories on Earth, by scientists analyzing data and developing theories, by all of us participating in humanity's greatest intellectual adventure, the quest to understand where everything came from. And finally, after thousands of years of wondering, we're getting real answers. That's something worth celebrating. That's something worth sharing. That's something worth being part of. Thank you for taking this journey through cosmic origins with me. If this video changed how you think about existence, share it with someone who needs to know. Subscribe for more explorations of the universe's deepest mysteries. And keep looking up. The cosmos has more secrets to reveal, and we're just getting started.